In the last episode, we saw what is the inverse of a matrix, and we kind of had a formula where the inverse of a matrix is given by 1 over determinant in the denominator multiplied by adjoint of the matrix. There is a concept which is closely related to the inverse of a matrix, which is called as singular or non-singular matrices. And what it means is, we know that when A and A inverse are multiplied, we have the product as unit matrix, right? But it is not necessary that every matrix is invertible, meaning it is not necessary for every matrix A inverse exists. Okay, for some of the matrices, A inverse may not exist. It may not exist. And what will happen in those cases is, if the inverse of the matrix does not exist, if you see this formula over here, which we saw in the last episode, which is the formula for the A, computing the A inverse. Let's say hypothetically there is a matrix for which A inverse exists. So there is the inverse of a matrix, or the matrix A is invertible. The inverse exists. In this case, when we apply this formula, the determinant will not be 0, because the determinant will have some value, positive or negative, but it cannot be 0, because if the determinant becomes 0, then the whole solution is undefined. Hence, the determinant cannot be 0 if it has to exist. So what does it mean? In other words, if this given matrix A is invertible, meaning the inverse of the matrix exists, then the determinant cannot be 0. Okay, the determinant cannot be 0. Such matrices where the determinant will never be 0, and hence the matrix is invertible, or there exists an inverse of a matrix, in other words, those matrices are called as non-singular matrices. Again, if a matrix is invertible, meaning there exists an inverse to the given matrix, then the determinant will never be 0 in such cases. Such matrices are called as non-singular matrices. On the contrary, if an inverse of a matrix does not exist, let's say if the inverse of the matrix does not exist, meaning the given matrix is not invertible, then what happens is the denominator at the bottom becomes 0, and hence the inverse does not exist. So in that case, the matrix is not invertible, and this kind of matrices are called as singular matrices or singular matrix, meaning that when you just take this word literally, singular, there are kind of exceptions. They are singled out. They are exceptions, right? So there are some matrices which are exceptional cases, which can be singled out, which cannot be inverse. They are not invertible, and hence the determinant is always 0. And these matrices are called as singular matrices. So that's a small concept of what is a singular versus non-singular matrix or matrices, and more kind of a visuals here. If you see a matrix is singular in the examination, if they ask you, hey, can you prove this matrix is singular or not? All you have to do is you have to find the determinant of the matrix, and if the determinant of the matrix is 0, then the matrix is singular. It can be singled out, whether it's a 2 by 2 or a 3 by 3. Simple determinant using any row, any column. That's what it is. For example, if you see some numericals here, we have a given matrix, and I'm taking a simple determinant by cross multiplying the diagonal elements, and the answer is 0. Hence, the inverse of this matrix does not exist. It's not possible to invert this matrix, or this matrix is not invertible. Similarly, this one on a 3 by 3. This is a singular matrix because the determinant of a 3 by 3 using this formula is 0. That means matrix A does not have an inverse. Whereas if you take this matrix B, the determinant is not 0. It's negative, but it's not 0. That means B inverse exists. So that's all it matters, whether based on the combination of whether determinant is 0 or not, or the matrix is invertible or not. Either way, if you find the determinant, you can prove one way or the other what's happening. And that's kind of a quick wrap up on singular versus non-singular matrices. Thank you.